We've now seen how to take a given surface and parameterize it, or understand what a parameterization is describing. So we have a surface, let's say capital S, that can be parameterized via, and then we use the notation R of uv. It's a vector valued function in two variables given by the vectors x of uv, y of uv, z of uv, right? And then D we'll call the parameter domain. Remember, this is possible u and v values that we can plug in to our parameterization of the surface. And what we can ask now is, well, now that we can express surfaces via some regularized or smooth parameterization, we can ask, well, now what would surface integrals look like, right? So we can use our knowledge of parameterizing surfaces to define both scalar and vector surface integrals. Let's start with scalar. Let's start with first defining a scalar surface integral, meaning the function that we're integrating over this surface is a scalar function, right? Versus when we look at vector surface integrals, the function that we're integrating over the surface is a vector field. And these both have their different interpretations and applications respectively. Let's start with trying to understand. So first, before we define the scalar surface integral, one really important concept that we should first understand is how to calculate surface area. So let's use this parameterization R of uv to calculate the surface area of a parameterized surface. So parameterized, sorry, I kind of ran out of room there, surface S. Now let's look at what we have. We have some parameter domain, uv. And let's say in this parameter domain, we'll call it D. We have U. Let's let D be the set of points U and V such that U is between A and B and V is between C and D. Okay. And what we'll have here is a rectangle that we can partition. And so let's just partition. You know, you can define a partition on the interval. So we take AB. Let's partition into M subintervals, right? And we can partition CD into N subintervals. And these partitions give us kind of an underlying grid of our domain. And we can break this, we can think about this grid then being, you take the, like, in conjunction, these two partitions define these subrectangles Dij here, right? And what we want to understand is, remember, what we're trying to do is calculate surface area of an arbitrarily complicated surface. And so we have this Dij's here. And how do we calculate surface area? Well, one way we're going to do it is under the function R, right? Under our vector valued function R, which represents the parameterization of this surface, it maps this domain D into a surface. Say, here's our surface S sitting in the XYZ coordinate system, right? Or in 3D space. The partition of our domain into these rectangles gives us a grid system over the surface, Sij. And we can look then at the subparallelograms generated by being the image of this Dij. So the Sijs here are, we've now kind of sectioned our surface. You can think about overlapping a grid over the surface, and then you're looking at like each little piece of the grid, right? This is the image of Dij under the function r, right? And so in this way, we have a grid over our entire surface S. And what we can do now is try to approximate the area of each little grid, like each little subsection here. Then you sum it up, right? And then let the grid become arbitrarily close together, or like an arbitrarily fine grid, and we'll get the area this way. And so we need a few more background pieces here. We'll notice that the width of this Dij, so the area of these Dij's is going to be delta U, delta V, where delta U is the partition, or the, excuse me, it's the distance between two partitions, right? Or between two pieces of our partition. And so these subrectangles Dij have width delta U, and they have height delta V here. We also want to indicate the lower left corner. We want to indicate the point that's the lower left corner of these rectangles Dij. We're going to call these points Ui star and Vj star. Okay. And we'll call the image of this point Pij. So the lower left corner of the parallelogram Sij is the point Pij here, which is, you know, if you'd like, Pij is equal to R of Ui star Vj star. Right. Okay. Now let's focus our attention to this Sij. And so what we have is some, whoops, I guess I could draw it in red, that'd be okay. We have some Sij here, which is just one piece that's kind of been defined by the image of the grid lines in the domain, right? And so we have this point Pij here. And now the question is, how could we approximate this area? We want the area. So the goal is to approximate the area of Sij, which we're going to call delta Sij. And how can we come up with an approximation of delta Sij? Well, you can see this is awfully close to a parallelogram. If we are traveling at this point Pij here, so if we're at the point Pij, we can travel in the direction where the surface is changing with respect to the parameter u, right? And this is exactly the vector r sub u. So we get this vector here, and we'll call it t sub u, and it's going to be defined to be, and so let me say this is t sub u at the point Pij. This is going to be equal to, well, we're observing at how the surface is changing with respect to u right here, right? And so this is r sub u at this point ui star vj star, right? Then we can also think about how the surface is changing with respect to the parameter v. And so we have another tangent vector, tv, which is, again, how the surface is changing in the v direction, or with respect to the v parameter. This is tv of Pij is equal to, now you take the v partial derivative of ui star vj star. And you can see, to get a good approximation for the area of this Sij, we can find the area of the parallelogram spanned by Tu and Tv. However, we do need to scale this. We need these to be at an appropriate length. So we need to scale these vectors accordingly. And so because of that, we want to find the area of the parallelogram with edges delta u Tu, because now we're scaling it by this delta u, right, to make sure that it's the appropriate length. And we're also going to scale Tv by delta v here. Okay, and well, how do we find the area of a parallelogram spanned by these things, right? Well, we take their cross product. We know the cross product of two vectors with the same initial point, their cross product, the magnitude of the cross product gives us the area of the parallelogram spanned by these vectors. And so this means delta Sij is approximately the magnitude of delta u Tu cross delta v Tv. You can see here, these sides are the two vectors that we're taking the magnitude of. And so they're these tangent vectors and then scaled to the appropriate length via multiplication by delta u and delta v respectively. Well, we know properties of the cross product and the magnitude that this is the same, this is the same as the cross product of Tu cross Tv, and delta u and delta v are constant. So these can be pulled out front or to the back. And so by convention, we'll just pull those to the back there. Then what this means is, well, if the area of each of these little sub Sijs here, if the area of these is approximately the area of these parallelograms, well, then the area of the entire surface is approximately the area of all of these parallelograms summed up. So we have then that, we'll say delta S is approximately double sum, I goes from 1 to m, j goes from 1 to n of, well, then the area is going to be magnitude of Tu cross Tv, delta U, delta V. And this leads us to the definition of the surface area. So we have a definition. The surface area of S parameterized by R of uv is, so I'll say surf of S. It's double integral over our parameter domain D of the cross product of TU cross TV du dv. This gives us a well-defined formula for calculating surface area just by understanding how we parameterize this surface. Remember, this is, so I'll write it on the next page, where, so remember if we have R of uv equals x of uv, y of uv, and z of uv, then the tangent vector in the direction where u is changing, right? The tangent vector in the u direction is given by dx, du, dy, du, dz, du, and tangent vector indicating change in v is dx, dv, dy, dv, dz, dv. And so what this formula is saying here is to calculate the surface area of a given surface, you need to first parameterize the surface. Then you need to calculate the partial derivatives with respect to u and with respect to v. You take their cross product, right? So we said, I'll rewrite this so it's all on one page. So the surface area of S is equal to integral over this region D of, again, what do we have here? We have that this is the magnitude of TU cross TV du dv. And so you have to calculate these T sub u and T sub v by understanding what the parameterization is and then taking partial derivatives. And then you have to take their cross product, then you take the magnitude, and then you have a double integral, and you can calculate surface area, which is relatively painless considering how arbitrarily complicated a surface could be. And we will use this idea here to understand what a scalar surface integral is calculating. And so now let's use this to define the scalar surface integral. Okay. So when we look at a surface, S, here's our surface again, S, the scalar surface integral, which will be indicated as, so the notation here, let me introduce notation. The notation is the scalar surface integral is you write double integral over the surface S of your function f of x, y, z, and then d capital S. This is notation for the scalar line integral. Okay. This is volume of solid above S and below the function f of x, y, z. And so how do we understand this here? Well, we have a surface S. We're looking at some function, however it's behaving, f of x, y, z. We can think about extending this surface kind of just vertically, and then looking at how this surface, or how the what solid is obtained between the surface and this function f of x, y, z. And the scalar surface integral is going to give us volume, right? This volume here Volume is the scalar surface integral. And so how do we calculate the volume of this shape? Well, we need the area of the base surface here. And so this volume is going to be the area of the base surface times the height. And now we just learned how to calculate the area of the base surface, right? The area of the base surface is this surface integral here, right? Or this integral to calculate surface area. And we did this by introducing a partition, and then we got these like sub regions here, right? And then so we calculated that like delta Sij was approximately the magnitude of Tu cross Tv du dv, or excuse me, delta u delta v, right? Where again, Tu and Tv were the respective tangent vectors, where you take the derivative of r with respect to u, and then the derivative of r with respect to v. Okay, and so we have the formula for the area, right? And so let's compute like a delta v here. Let's compute the area or the volume of a solid just over this delta Sij, right? And so delta v is going to be equal to the height times this delta Sij, right? But what's the height going to be? Well, we had a point that we could examine, right? We have this point Pij for every rectangle Sij. And so the height can be given by looking at the function at Pij. This height here is, the height is f of Pij. This gives us an approximation for the height, and this gives us an approximation for every sub prism or sub solid here, right? And so the delta v here is going to be approximately f of Pij times delta Sij, which we learned was the magnitude of u cross, or T sub u cross T sub v, delta u delta v. And this means the volume is approximately the double sum, where I goes from 1. So now we sum over all of these, right? We have this grid here like this. And now we take the sum over all of these, like the volume over every single sub-parallelogram here. And this is I goes from 1 to m, j goes from 1 to n, f of Pij times the magnitude of Tu cross Tv, delta U, delta V. And this means that the volume is exactly, once you take these limits, these partitions become arbitrarily fine, and this becomes an equality. So we have the limit as m and n go to infinity of the double sum I goes from 1 to m, sum j goes from 1 to n, f of Pij times magnitude Tu cross Tv, delta U, delta V. And this gives us a definition of the scalar surface integral. Okay, so the scalar, surface integral of f of xyz over s is, and we write double integral over s of f of xyz ds. This is equal to, so I can already tell I'm going to need more room because I tend to write big. So let's say s f of x, y, z ds. This is the limit is m and n go to infinity of the double sum. I goes from 1 to m, j goes from 1 to n, f of pij, magnitude of tu cross tv du, or delta u, excuse me, delta v. And this limit we can express in a slightly different way. More importantly, we have that the double integral, the scalar surface integral, is equal to the double integral over our parameter domain D of f of r of uv times the magnitude of tu cross tv du dv, where, again, where, so this is scalar vector, or scalar surface integral, sorry. Yes, where remember that r of uv is x of uv, y of uv, z of uv, and the tangent vectors t sub u and t sub v are respectively given by the partial derivatives with respect to each parameter. So t sub u is dx, du, dy, du, dz, du, and tv is dx, dv, dy, dv, dz, dv. Okay, and so this here is a nice representation of what a scalar surface integral is, what it's calculating, and how to calculate it. So you have to understand the parameterization of your surface. You have to be able to take partial derivatives, and then you have to plug it into a double integral. Okay, so let's do an example, and then I think we'll break there and have to make a part 3 because there's a lot to talk about for surface integrals, and we won't have even gotten to vector surface integrals. So let's do an example. Let's calculate the scalar surface integral of x plus y squared ds, where s is the surface. So let's see here, where s is the cylinder, x squared plus y squared equals 4, and we're looking at z between 0 and 3. Okay. So it always helps to understand the geometry of what's going on here. And so we have a circle of radius 2 that is independent of z value, right? And so at any height, this is a circle of radius 2, which means we have a right cylinder of radius 2, and then we're going between z equals 0, which is the xy plane, and z equals 3. Say this is 3 up here. And so we have this cylinder here. And we want the surface integral of the function x plus y squared over this cylinder. So first we need to parameterize this cylinder, right? And remember, we can parameterize a cylinder of radius r by r cosine v, or let's use u. I think in my notes I use u, I like that better. So r cosine u, r sine u, and then the height, right, which we can use this parameter v just to directly indicate the height, right? And again, I'm using one parameter v to indicate height, And then I'm using the parameter u to indicate what is the picture, what does the two-dimensional trace look like at that height, right? And so when I'm at a given height v, I look at the plane z equals v, and then I see that it's a circle of radius 2. And then so I use u to parameterize a circle of radius 2 here. Okay, and let's remember our formula, right? We need, in our formula for a scalar surface integral, first we need f of r of uv. So let's calculate f of r of uv. Well, f is x plus y squared. And so if we plug in x plus y squared, we're going to get 2 cosine u plus 2 sine u quantity squared, which is 2 cosine u plus 4 sine squared u. So this is our f of r of uv here. What do we need next? We also need tu and tv, and then we need their cross product, and then we need the magnitude of the cross product. So t sub u, let me copy what r was again. Remember, r was 2 cosine u, 2 sine u, v. Then t sub u is the partial derivatives with respect to u. So negative 2 sine u, 2 cosine u, and 0. And then the partial derivatives with respect to v give us the tangent vector tv, which is 0, 0, 1. Right? Because there's no v's in the x and y components, and in the z components, the derivative of v is just 1. And now we need their cross product. Tu cross tv is, well, we have to set up the 3 by 3 matrix, ijk, negative 2 sine u, 2 cosine u, 0, and then 0, 0, 1. Taking the cross product here, we see that we'll get 2 cosine u I hat minus negative 2 sine u j hat. And then the k hat vector will be 0 plus 0 k hat. And so tu, we've learned that tu cross tv is the vector 2 cosine u, 2 sine u, 0. And now we need the magnitude of this vector. Whoops. So this is equal to square root of 2 cosine u squared plus 2 sine u squared plus 0 squared, right? Just remembering what tu cross tv is. This gives us square root 4 cosine squared u plus 4 sine squared u, which is equal to root 4, because you pull out a 4, and then cosine squared plus sine squared is 1, and then root 4 becomes 2. So using our formula, the scalar surface integral of x plus y squared ds is equal to, well, let's just remember, double integral over the parameter domain d of f of r of uv times the magnitude of tu cross tv du dv. Well, what's the parameter domain, right? Well, this is a cylinder, and we're going all the way around the cylinder, and the trig functions are in the function, or in the parameter u. So we have u going from 0 to 2 pi, right? Because we're sweeping all the way around the cylinder. And then we have the parameter v, which is exactly z, right? We have here z equals v, and z goes from 0 to 3, so that means v goes from 0 to 3. And so our parameter domain d is u goes from 0 to 2 pi, v goes from 0 to 3. And then we learned that f of r of uv was, where did we go? 2 cosine u plus 4 sine squared u. So we have 2 cosine u plus 4 sine squared u, and then times the magnitude of tu cross tv, which was 2 du dv. And now this integral is not bad to solve. You just split it up over the sum, and then you take the integral of cosine and then the integral of sine squared. And I would strongly recommend you to finish this integral, and you can verify that what you should get is 6 pi. Okay, so here's an example of calculating a scalar surface integral, right? And it boils down to knowing this formula here. You need to be able to know, you've got to know this formula along with being able to understand how to parameterize a surface and how to calculate tangent vectors. And then once you have all that in place, it's just plug and chug, right? You plug it in and then you do the double integral. Okay. So now that we've seen how to understand, define, and use scalar surface integrals, we're going to do the same thing for vector surface integrals. So we'll go through a similar construction in the next video to discuss vector surface integrals, which is integrating a vector field over a surface.